Every time you pull out your phone to query an AI or stream a high-definition video or even just run a complex piece of software, something physical actually happens.
Right.
A processor somewhere out there in the world wakes up, crunches the numbers, and generates heat, like real physical burning heat. And
Yeah.
right now we're generating so much of it that we have to ask a serious question. How do we stop the internet from literally melting?
Yeah. It's a massive problem.
So to answer that, we are unpacking a really fascinating new white paper today from Supermicro, all about their DLC-2 architecture. That stands for direct-to-chip liquid cooling.
Exactly.
Our mission on this deep dive is to understand how swapping out traditional air cooling for liquid is, well, totally revolutionizing data centers. We're talking power savings, water savings, and completely altering the physical footprint of the whole tech industry.
It really is this invisible physical reality for most of us. We think of the cloud as this weightless, cool thing hovering somewhere out of sight.
Yeah, just magic.
Right, magic. But the ground reality is incredibly hot, and it's getting hotter by the minute. The infrastructure we've relied on for decades is, well, it's hitting a hard physical wall.
But before we look at the specific hardware that's swooping in to save the day, we kind of need to understand why the old way of doing things is suddenly failing us. I mean, basically just blowing really cold air over computers.
Yeah.
It seems like fans have worked fine since the dawn of personal computing, right?
Well, yeah, but it comes down to a metric called TDP, or thermal design power.
Right.
Essentially, this is the absolute maximum amount of heat a computer chip generates under a really heavy workload. And the cooling system has to dissipate that heat to prevent the chip from, throttling its performance.
Or in extreme cases, literally cooking itself.
Exactly. Literally cooking. And with each new generation of GPUs and CPUs, especially with the intense sustained math required for modern AI workloads, those TDPs are just rising astronomically. We are cramming vastly more processing power into the exact same microscopic surface area of silicon. So the byproduct of all that electrical activity is a massive, highly localized amount of heat.
Okay, let's unpack this. Because if the chip gets too hot, the internal resistance goes up, it draws even more power to do the same math. And eventually, the built-in safety mechanisms force the processor to slow down, right?
Yes.
You essentially lose the performance you just paid millions of dollars for.
Precisely. And traditional air cooling simply cannot keep up with this new generation of chips. I mean, air is actually a terrible thermal conductor. It's an insulator.
Huh?
Think about a puffy winter coat, right? It keeps you warm because it traps a layer of dead air around your body. So trying to cool a densely packed server rack with air is, it's highly inefficient.
Right, it's like trying to cool down a scorching hot cast iron pan by just blowing on it versus running it under the tap in the sink. The water instantly pulls the heat away.
That is exactly it. Liquid is fundamentally vastly superior to air at removing heat from hot surfaces. It has a significantly higher heat capacity and thermal conductivity.
Makes sense.
So in a liquid-cooled system, the supply liquid flows directly over the hot components. It absorbs the thermal energy from the silicon almost instantly. Then, that now warmer liquid is pumped away to an external cooling system, exchanges its heat, and returns to the servers in this continuous closed loop.
Well, wait, mixing liquid and highly sensitive, hyper-expensive electronics sounds like a recipe for absolute disaster. I mean, we're taught from childhood to keep water as far away from the computer as possible.
Absolutely.
A single leak in a rack containing millions of dollars of AI GPUs seems like an unacceptable risk for a data center operator to take. Why are they forced to take this leap now?
It does feel deeply counterintuitive, and the hesitation in the industry was very real for a long time. But these are meticulously engineered, closed-loop systems. They have sophisticated leak detection, negative pressure mechanisms, highly secure couplings.
Okay, so they've engineered away the risk.
Mostly, yes. But the reality is, operators are forced to take this leap because of sheer mathematical necessity. If you want the computing power required to train today's AI models, you have to use these specific new chips.
Right.
And if you use these chips, they will overheat and throttle if you only use air. I don't care how fast you spin the fans. The industry's hand hasn't been forced by a desire to innovate just for innovation's sake. It's been forced by the laws of thermodynamics.
Wow. So if physics is forcing this transition, it makes me wonder how the industry actually measures the success of swapping to liquid. In this white paper, Supermicro breaks this down into 4 measures of liquid cooling effectiveness.
Yes, the effectiveness metrics.
Yeah, and the first two seem to focus heavily on the physical footprint and the power grid impact of these facilities.
Let's start with the power grid impact, which is measured by PUE, or power usage effectiveness.
Right.
This is like the gold standard industry metric for data center efficiency. You calculate it by taking the total power entering the entire data center facility and dividing it by the power actually used by the IT equipment, the servers themselves.
So if a facility has a PUE of 1.0, that would mean 100% of the electricity coming from the power plant is going straight into the processors, with zero waste on lighting or cooling or building operations.
Right, which is mathematically impossible in the real world.
Sure.
But traditional air-cooled data centers sit around a PUE of 1.5. Think about what that actually means.
Okay.
For every single megawatt of power used by the servers to do actual computational work, another half a megawatt is consumed just to run the massive industrial air conditioning compressors, chillers, and giant fans required to keep those servers from melting.
Wait, so a full third of the building's massive power draw is just moving air around?
Yes, exactly a third. But Supermicro's liquid-cooled data centers, however, hit a PUE of 1.1.
Wow. The overhead drops from 50% down to just 10%. That translates to a massive 40% power savings on cooling across the entire facility.
It's huge.
When we talk about data centers consuming the equivalent power of small cities, a 40% reduction in cooling overhead is a staggering amount of electricity being given back to the grid.
You are virtually eliminating the electrical overhead of cooling. But the physical ramifications of this get even more dramatic when you look at the second metric.
SUE.
Right, SUE, or space usage effectiveness. This measures the actual physical volume required to house the computing power.
Here's where it gets really interesting, because the white paper points out that a standard air-cooled server designed for these intense AI workloads takes up 10 U of rack space.
Right.
And for context for you listening, U is a standard unit of measurement for server height. It's about 1.75 inches. So a 10 U server is a pretty chunky piece of hardware, roughly 17.5 inches tall.
It is.
But the liquid-cooled equivalent running the exact same processors takes up only 4 U.
Yeah, so a liquid-cooled rack is 60% denser. You are only using 40% of the vertical space compared to the air-cooled equivalent.
That's crazy.
Freeing up 60% of the physical space completely alters the real estate economics of the tech industry. I mean, you can put more than double the computing power in the exact same square footage.
Right.
When you're building a billion-dollar facility, doubling the compute density per square foot fundamentally changes your return on investment.
But wait, hold on. If we are squishing a massive 10U server down into a tiny 4U box and then craning entire racks full of these newly shrunken servers, aren't we just creating a much denser, vastly more dangerous box of concentrated heat?
Well,
I mean, if you pack a room full of highly dense space heaters, I don't care how efficient the chips are, that room is going to turn into a high-temperature oven. How does the building handle that?
that is the exact paradox of density, and it highlights why the physical liquid is the only way this works. An air-cooled building could never handle that level of heat density.
Because the air would just get too hot.
Exactly. The ambient air temperature in the room would skyrocket to dangerous levels immediately. But in a direct-to-chip, liquid-cooled system, the concentrated heat never actually enters the air of the room. It gets trapped in the liquid right at the surface of the chip and is carried away in an enclosed pipe.
So the room itself doesn't actually get hot because the heat is being smuggled out through the plumbing before it can radiate into the air.
Exactly. The thermal energy is entirely contained within the fluid path.
That is wild. And, you just mentioned eliminating the overhead of cooling and carrying the heat away in pipes. That naturally makes me wonder about the broader environmental impact, specifically regarding water.
Right, the third metric.
Yeah, the white paper introduces a metric called WUE, or water usage effectiveness. It claims this DLC-2 liquid cooling architecture uses about 40% less water overall. But wait, we are literally pumping water into the server racks now.
Yeah.
How were the old air-cooled systems wasting more water than a system that physically runs on water?
It sounds like a contradiction, doesn't it? But when we say an older data center is air-cooled, that just means they blow cold air onto the server chassis inside the server room.
Okay.
But the mechanism to get that air so cold in the first place relies heavily on water. Traditional data centers use massive evaporative chillers and cooling towers up on the roof.
Oh, I see.
They consume millions of gallons of municipal drinking water, constantly boiling it off and evaporating it into the atmosphere to create the chilled water loop that then cools the air.
So the air conditioning infrastructure itself is drinking all the water just to make the air cold enough to blow on the servers.
Precisely. With DLC-2, the water goes directly into the IT systems in a closed loop. It isn't being constantly evaporated into the sky to chill air. And here's the real game changer. The system uses warm water.
Wait, warm water? You are trying to prevent a supercomputer from melting down, and you use warm water.
Because liquid is so profoundly efficient at absorbing heat, the water entering the server doesn't actually need to be hyper-chilled. Ambient temperature water, say, around 30 to 40 degrees Celsius, can easily absorb heat from a processor that's running at 80 degrees Celsius.
That makes sense.
Because you aren't trying to force the water temperature down to near freezing levels, you eliminate the need for those massive, power-hungry water evaporating chillers entirely.
Wow.
A simple dry cooling tower, which works a bit like the radiator in your car, is often enough to reject the heat into the outside air without consuming any water at all.
That drastically shifts the economics.
Yeah.
Which brings us to the final effectiveness metric. Supermicro outlines UA, or money usage effectiveness.
Yeah.
This is essentially total cost of ownership.
Right.
When you compound the 40% lower power consumption from turning off the giant AC units, the 60% smaller physical footprint, meaning you build a smaller facility, and the 40% reduction in municipal water usage. The white paper calculates a 20% lower total cost of ownership over time.
It's massive. You pay less for electricity every month, you pay less for water every month, and your initial capital expenditure for the building itself is vastly reduced. Because, again, you need significantly less square footage to house the exact same amount of computing power.
So, if pumping warm water into ultra-dense racks saves all this money and prevents meltdowns, I am trying to picture what this hardware actually looks like when you pop the hood. How is the water physically touching these components?
Well, the flagship hardware Supermicro highlights is the SYS422GS NBRT LCC server. As we established, it's a highly dense 4U form factor, but what it holds inside is staggering.
Yeah, the specs are wild.
It houses two Intel Xeon 6 series processors, which act as the main brains of the system. Those can draw up to 500 watts each.
And it also holds an NVIDIA HGX board populated with 8 B200 GPUs. The B200 is like the premier chip driving the current AI revolution, and each one of those 8 GPUs can draw up to 1,000 watts.
Yes.
That is 8,000 watts of power just for the graphics processors running through a single 4U box.
Managing that kind of localized thermal load is incredibly difficult. Supermicro isn't just dropping a liquid block on the main processors and calling it a day.
Right.
They have designed bespoke cold plates that physically cover almost the entire motherboard architecture. They cover the CPUs and GPUs, but they also cover the PCIe switches.
The PCIe switches being the high-speed data highways that allow the GPUs to talk to each other and the rest of the system without bottlenecking. I imagine if those overheat, the whole data pipeline slows down.
Exactly. They also liquid cool the DIMMs, which are the system's short-term memory modules. And crucially, they cool the VRMs, or voltage regulator module.
Power traffic costs.
Right.
When you are pulling a kilowatt of electricity into a single chip, the components responsible for stepping that voltage down and delivering it cleanly generate an immense amount of secondary heat.
By engineering these custom cold plates to cover every single component that generates significant thermal energy, they are capturing up to 98% of the system's total heat directly into the liquid loop.
So what does this all mean? It sounds like instead of blasting air conditioning into a crowded room, they're putting a bespoke circulatory ice pack directly onto every single vital organ of the machine.
That's a great analogy. Because they capture 98% of the heat at the microscopic source, the ambient air in the server room is practically irrelevant now. The servers just aren't rejecting heat into the aisle.
To handle all that heat being pulled away in the liquid, the architecture relies on in-rack CDUs, or coolant distribution units. These are essentially the pumping hearts of the system, right?
Exactly.
The new CDUs can remove 250 kilowatts of heat per single rack. The white paper notes that's a 150% increase in capacity over older 100 kilowatt units. 250 kilowatts of heat in one rack is the equivalent of running roughly 160 residential space heaters on full blast inside a space the size of a refrigerator.
It's unbelievable density, and this is where that warm water capability becomes critical. These servers and CDUs are rated to handle water inlet temperatures up to 45 degrees Celsius. That is 113 degrees Fahrenheit. You are effectively cooling state-of-the-art supercomputers with water that is hot enough to take a bath in.
And the white paper also mentions hybrid cooling towers that sit outside the facility. They adapt to seasonal changes, using dry tower mechanics in the winter when the outside air is cold enough to chill the loop, and seamlessly engaging standard evaporative features only during the peak heat of summer.
Right, it's very efficient.
But beyond the thermal specs, there's a physical side effect of capturing 98% of the heat in liquid that I found completely surprising: the noise reduction.
Oh, yes. Because the liquid is doing almost all the heavy lifting, you no longer need giant, high RPM industrial fans screaming at top speed to force massive volumes of air through the dense chassis.
Right.
The internal fans can run much slower just to create a gentle breeze for that remaining 2% of ambient heat.
The servers operate up to 25 decibels quieter, bringing the noise level down as low as 50 decibels. Anyone who has ever stepped inside a traditional high-performance data center knows that the roar of the fans is deafening.
Oh, it's brutal.
It sounds like standing on the tarmac behind a jet engine. You literally have to wear industrial ear protection to walk the aisles safely. But 50 decibels is roughly the ambient hum of a quiet refrigerator or a moderate rainfall.
It's a staggering difference. But, building a silent, hyperdense room with bespoke motherboard cold plates, in-rack fluid distribution units, and hybrid external cooling towers sounds incredible on paper.
Sure.
But it also sounds like an absolute logistical nightmare to actually construct and plumb in the real world.
And that brings us to the logistics of deployment, or what the industry measures as TTO.
Right. TTO stands for time to online. In the current technology landscape, particularly with the hyper-competitive AI arms race, speed is everything.
Oh, absolutely.
It's not just about saving money on your utility bill. It's about getting your computational capacity up and running, generating revenue and training models before your competitors do.
The solution outlined in the paper is called Data Center Building Block Solutions, or DCBBS. It is an end-to-end integration package.
Yes.
They provide the servers, the racks, the networking gear, the storage, the internal manifolds, the liquid piping, the external cooling towers, and the management software. By providing it all as a single pre-engineered package, they shrink a typical 12-month data center deployment process down to just 3 months.
3 months is incredibly fast.
But how on earth is installing custom plumbing, liquid distribution units, and external water towers 9 months faster than just rolling a bunch of traditional air-cooled racks into a room and plugging them into the wall? It seems like adding water to a building introduces massive construction friction.
Well, if you were trying to piece this together using traditional procurement, buying servers from one vendor, racks from another, hiring local pipe fitters to custom walled plumbing on site, trying to integrate third-party cooling towers,
Right.
It would be a friction-filled nightmare.
Right.
But the building block approach means you aren't doing custom engineering on site. It is more like a modern modular home.
Oh, I see.
All the complex internal piping, the manifold connections, and the server integrations are pre-fitted and tested in the factory. When the racks arrive at the data center, the operators just connect the main utility lines and turn it on.
So the integration friction is resolved in the manufacturing facility rather than on the concrete floor of the data center.
Exactly. And the business reality of this timeline cannot be overstated. We are talking about deploying racks populated with NVIDIA B200 GPUs.
Yeah.
These are currently some of the most sought-after, highly constrained, and strategically vital pieces of hardware on the planet. Having a 9-month head start on deploying that magnitude of AI processing power isn't just a nice operational efficiency for the IT team.
Right, it's everything.
That 9-month gap could literally mean the difference between a company leading the global market in artificial intelligence or becoming entirely irrelevant.
It really puts the race in AI arms race into perspective. The timeline is just as critical as the thermal physics.
It shows that liquid cooling is no longer a science experiment or a niche bespoke solution reserved for government supercomputers. It has become a fundamental operational requirement for participating in the modern tech economy.
So we started today by looking at the harsh reality that today's chips are simply running too hot for air to handle, forcing the industry to rethink its basic infrastructure. We explored how highly dense 4U servers use bespoke cold plates to act as a circulatory system, capturing 98% of the heat right at the silicon surface.
And we saw how cooling those components with 45 degrees Celsius water fundamentally alters the economics of a facility, saving 40% on overall power by turning off the giant AC units, and saving 40% on water usage by eliminating evaporative chillers.
And we learned that by utilizing pre-optimized modular building blocks, this entire fluid-driven architecture can be brought online in just 3 months, granting a massive competitive advantage in the AI market. It really is a complete paradigm shift in how we build the internet's physical backbone.
It really is.
I want to leave you, our listener, with a final thought to ponder. Something that wasn't explicitly laid out in the white paper, but is a direct consequence of this shift.
The downstream effects of this density are fascinating to consider.
Yeah? If liquid cooling completely eliminates the need for massive roaring HVAC systems, and if it shrinks the physical space required for computing by 60%, and if the servers themselves are now running at a quiet 50 decibels instead of a deafening roar, will the data centers of the future stop looking like giant, loud industrial warehouses out in the middle of nowhere?
That's a great question.
Could they become completely silent, ultra-dense, fluid-driven black boxes hidden right inside our office buildings, our apartment complexes, and our cities? The next time you pull out your phone to query an AI, and that physical heat is generated, it might not be happening out in the desert. It might be happening quietly in the walls of the building right next door. Thank you so much for joining us on this deep dive. Keep questioning and stay curious.